Welcome back to Chem 4300. In this video we're going to begin Chapter 11 on wave mechanics, and it's in this chapter that we're going to learn the mathematical formalism for doing quantum mechanical calculations. So let's begin. Now, we learned in the previous chapter that matter has wave and particle-like properties, and the relationship between those properties was worked out by de Broglie, who gave us this simple formula here, that a particle that has some momentum will also have a wave-like property that has some wave number or wave vector associated with them. And the relationship between them is simply Planck's constant divided by 2 pi. So this is what we learned in the last chapter. Now, in the chapter on classical waves, we also learned that the wave function as a function of position has an equal representation as a function of wave number. And that transformation between those two representations is the Fourier transform. So I can take the wave function as a function of position and turn it into the wave function as a function of wave number. Both are equally valid. And of course, this is the inverse transform and the forward transform here. But what we see then is that if we have our de Broglie relationship that tells us that wave number or wave vector is related to the momentum, then we can replace the wave number here in these expressions with momentum and find the relationship between the wave function as a function of position and the wave function as a function of momentum. So if you do that substitution, a little bit of algebra, but you get this result here. So we see that there is a Fourier relationship in quantum mechanics between the wave function as a function of position and the wave function as a function of momentum. All right? So that's a very important thing to keep in mind, and we're going to use this to calculate other properties of the system based on its position and momentum and energy and so on. All right. So now let's look at something that's really going to be important, is understanding how to use something called operators in quantum mechanics. So let me just start out with a very simple case that you already know. We learned in the classical wave chapter how we could look at, say, the mean position of a wave by taking the wave function and squaring it, normalizing it, and then integrating it. Normalizing it to get a probability function and then integrating over all space to find the mean position of the wave. So we're going to do the same thing here in quantum mechanics. If we want to get the mean position of the wave function, we're going to take the wave function, multiply it times the probability function, and integrate it over all space. Now, in quantum mechanics, the wave function times its complex conjugate is going to give us the probability density. So that's going to work out to be this integral right here. Now, we also define then in quantum mechanics something called an operator. And an operator does this job. It operates on the wave function, and in this case, if x operates on the wave function in the x basis, it simply gives you back x, a number, not an operator, a number, times the original wave function. Okay. So in the formalism of quantum mechanics, what we're going to do is we're going to write this expectation value starting in this form here as this sandwich. In other words, we're going to put the x operator between the wave functions, and we're going to first apply this operator to the wave function to the right. And when it applies to the wave function on the right, we get back the position times the wave function. And now that it's no longer an operator, we will slide it past the other wave function to move it out here. And then, of course, this product is the probability. And that's the same thing that we had before. Now, you might look at this and think, that seems quite a lot of work to do what we already had before. But just hold on. Hold that thought, OK? So we could do the same thing with any kind of function of x. So if we wanted to get the mean value or expectation value of x squared, we would define an x squared operator, place it in the sandwich there, and then we would apply it to the wave function, get back the value squared, and now that it's no longer an operator, we can slide it past the wave function, and it sits over here, and this product here is the probability, and we have our calculation of the expectation value for x squared. Even if we had some function of x, we can define a function operator if we like. So we can say f is some function of x. When it applies to the wave function, we get back some value that evaluated for those positions, and then it can now slide past the wave function to go over here, where now we have the probability, and now we're just doing this integral, a weighted integral of the function for over all possible values of x. All right. So this is going to work as long as f is a function of only x and not a function of momentum, and you'll see the reason for that shortly here. Again, you're probably wondering, okay, this all makes sense, but what's the point of making this, adding these extra steps here? Well, let's keep going here and look at momentum. So let's say we want to calculate the mean or the expectation value of a particle's momentum. We would adopt the same approach as we just did with the mean position, except now we're going to use the wave function in the momentum basis instead of the wave function in the position basis. And everything is going to look otherwise exactly the same. So in other words, I'm going to define a momentum operator which will act on the wave function in the momentum basis and give me back a number, the momentum, times the wave function. This is no longer an operator, so it can slide past the other wave function, and now I get p times this square of the wave function, which is a probability density, integrated over all values of momentum, and I get the mean or expectation value for the momentum. But this case, the operator p applies only to the wave function in the momentum basis. So it applies to the wave function in the momentum basis, gives me back a number times the original wave function. I could do this for the p squared operator. I could do some function of p, and this will all be analogous to what we did with x. But again, we just sort of added all these extra steps, introduced this operator notation to get a result that you probably would have worked out without introducing all this. But now we have the reason why we're doing this. So let's go on to the next slide here. What if we wanted to calculate the expectation value for the momentum, but using the wave function in the position basis? So we would still create this sandwich here with the wave function, the operator, and the wave function, and this will have to give us the same result as if we use the wave functions in the momentum basis. But now we have a challenge here, because you look at this and you say, well, I know what p does on the momentum basis wave function, but what does p do when it operates on the position basis wave function? And that's what we have to figure out. So let's see how we're going to do that. Well, what we realize is that we know how p operates on the momentum basis, and we know there's a relationship between the wave function in the position basis and the wave function in the momentum basis, and that's simply the Fourier transform, right? So if I'm operating p on the wave function in the position basis, then that can be turned into just putting p on the Fourier transform relationship here, and that would give me now p operating on the wave function in the momentum basis, where I already know what the answer is going to be. So that's how we're going to solve this. But we're going to take this one step further here and see if we can find a way to just evaluate this directly without having to go through this step. So what I'm going to do is I'm going to take the derivative of the Fourier Fourier expansion of the wave function in the position basis. So here it is, and I'm going to take the derivative with respect to x. And if I take the derivative with respect to x, then you can see that the only thing that depends on x is this e to the ipx over h bar here. So when I do that derivative, I get ip over h bar times back the original function here. And written in this way, I can pull that ih bar out, and what I have left over is that term that I just created up here. So this term is the same as this term, which is equal to the p operator operating on the wave function in the position basis with the additional factor of I over h bar. So just bring all this down left and far right. I have this relationship between the derivative of the wave function with respect to position and I over h bar of the momentum operator operating on the wave function in the position basis. Let's take this, hold that, take it to the next slide, rearrange it, And what you see is that when P operates on the wave function in the momentum basis, in the position basis, what it does is it takes the derivative of the wave function with respect to x and multiplies it times minus I h bar. That's the operation of P on the other basis, not on its momentum basis wave function, but on the position basis wave function. So that's the answer to this question here. What happens when we operate on the other basis? Well, it ends up taking the derivative of the wave function and multiplying it times IH bar. And this is one of the reasons why we have to introduce this operator notation, that we have to keep the operators separate and applied only to the wave function in that sandwich like we did. So what we're going to do now is we're going to define this generically as the momentum operator operating in the position basis. Okay? This allows us to work all of our problems in the position basis, whether we're working with x position or momentum or later energies. We're going to stay in this basis, and we know anytime we encounter the momentum operator, we will use this instead of the definition that we learned, the simple definition we learned when it operates on the momentum basis wave function. So I'll leave it as an exercise for you to determine the position operator in the momentum basis, so the opposite problem. You should get something analogous to that. And then one other thing I want to mention here is that generally speaking, in quantum mechanics, whenever an operator operates on a wave function and you get back the original wave function times a number, then we say that that wave function is an eigenfunction of the operator, and the value you get back is the eigenvalue of that operator. So it's very similar to what we learned when we were diagonalizing matrices. We have eigenvectors and eigenvalues, so this is analogous to that there. Now, so that's one thing that's important. So now you see that if we talk about the wave function in the position basis, we know that that is an eigenfunction of x, right? Because we know that x applied to the wave function gives back a number x times the original wave function. So that is an eigenvalue of x. Similarly, the wave function in the momentum basis is an eigenfunction of the momentum operator, because we know if it operates on that, we get back a number, the momentum, times the original function. That's obviously an eigenfunction of the momentum operator. But now we've learned that if P operates on the of the wave function in the position basis, that when it operates, it ends up taking the derivative, and you may not, very likely, get back the same function. So it is not then an eigenfunction of the momentum operator. So the position basis eigenfunction is not an eigenfunction of the momentum operator. Similarly, you can show that the wave function in the momentum basis is not an eigenfunction for the x operator, the position operator, and I'll let you prove that one at home. So finally, the last thing I want to say in this video is that all the operators that we're going to be dealing with in quantum mechanics have to be linear operators. In other words, when you apply an operator to a wave function, it can only give you back linear differential equations involving that wave function. So some kind of behavior like this here. In other words, we're not going to have operations that are going to cause you to take the square root of a wave function, or the log, or sine or cosine, or raising it to some power other than 0 or 1. So those are all not going to be allowed. It has to lead to a linear differential equation involving the wave function. So that's it for this section here, and in the next video we'll look at uncertainty principle and commutation relations.